Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 5 of the series on linear relations, and we'll be discussing how to find the solution set for the intersection of two lines in the Cartesian plane using the method of substitution, aka MOS, and the method of elimination, aka MOE. We'll start off by looking at question 4, and it says that we should be using MOS, method of substitution, to find the point of intersection of the following two lines. This is the maple output for the problem, so disregard this for the time being. That was generated by maple, but the system at hand is this system right here. Line 1 is minus 1/2 x plus 3/4 y equals 17 over 4. And line 2 is 1/3 x minus 1/4 y equals minus 25 over 12. And the first thing you'll notice is that we have a lot of nasty fractions going on. Okay, so in the next slide, we'll discuss how to deal with these fractions. Again, we have the same problem. Line 1 is negative 1/2 x plus 3/4 y equals 17 over 4. And line 2 is 1/3 x minus 1/4 y equals minus 25 over 12. And we're going to be using the method of substitution to get a solution to this linear system. Recall that this is called a 2x2 linear system. This is a linear equation in x and y. This is another linear equation in x and y. And these two equations need to be solved simultaneously. So we have a 2x2 linear system that needs to be solved simultaneously. The first order of business over here, if you don't want to go crazy, is to clear the fractions. We look at the LCD of all the fractions appearing. We have 2, 4, and 4. The LCD is 4. What we're going to do is multiply the equation right across by 4 to clear all the fractions. Okay, when we do that term by term, we get 4 dot negative 1/2, which is negative 2. And then 4 dot 3 over 4, the 4's cancel, and you get 3y. And 4 dot 17 over 4, the 4's cancel, and you get 17. So we've cleared the fractions readily for this one, so it doesn't look quite as nasty as it did in the beginning. So the idea is that when you have fractions present in the coefficients or the constant term, it's really a good idea to clear the fractions first using the lowest common denominator. We'll turn to L2. We have 1/3 x minus 1/4 y equals minus 25 over 12. Again, nasty fractions. The LCD of 3, 4, and 12 is 12. And we're going to multiply the equation right through by 12. Perfectly legitimate. You can take any equation and multiply through by any constant. As long as you do it term by term, that's a completely legitimate operation. So that's what we're going to do. We're going to multiply by 12 term by term to clear the fractions. So we have 12 dot 1/3 is 4, so we get a 4x. 12 dot minus 1/4 is minus 3, so we get a minus 3y. And 12 dot minus 25 over 12, the 12's clear, and you get minus 25. So these look a lot better than the originals. And that's really what I would do to start off with. You could solve the system without clearing fractions. The decimals get a little bit nasty, or the fractions get a little bit nasty to deal with, so I wouldn't recommend it. So remember to clear the fractions first in the event that you've got a lot of fractions in your linear equations. So now we're going to be dealing with the equivalent system. There's line 1 right there. There's line 2 right there. Completely equivalent to the originals. And now what I'm going to do is look for the plus minus x or y term. Over here the coefficients are minus 2 and 3. Neither of them are any good. The coefficients over here are 4 and negative 3. Neither of them are any good. So we have to choose a single term at random and proceed from there. This is the problem with the method of substitution. You can arbitrarily choose. I chose to zero in on the 3y term over here. We could have chosen minus 2x, 4x, or minus 3y. Completely up to you. I chose to deal with the 3y first. The objective is to solve this equation here for y. So I left the 3y over on the left. I moved the minus 2x over to the right. When you do that, you get 3y equals 17 plus 2x. Again, the order is irrelevant. I could have put the 2x up front. Completely irrelevant. It's completely up to you. And then what you do over here to get rid of the 3 is you divide term by 3. Okay, so you're going to divide this equation term by term by the number 3. When you do that, the 3 clears on the left. You get 17 over 3, and then plus 2/3 x. And now it's time to transfer the goods over to the right-hand side. We have y equals something, so we zero in on the y term here, and we're going to make a direct substitution. So in the next line, this reads 4.x minus 3 bracket, and we grab this guy and substitute it in for y, and then equals minus 25. Now we have a bullet and 2 targets. Again, make sure you use brackets, because failure to use brackets is going to cause a catastrophe at the end. Guaranteed. Okay, so please use brackets. Now we have a bullet and 2 targets. We're going to fire that bullet at each target. And actually, I do it quite rapidly over here because I automatically assumed that you're getting the hang of backward bin gathering, because that's what I do in the next step. I do this on the fly. What I do is open up an X bin on the left, because the objective is to solve for X. I pick up a 4 here, and when you distribute over here, you get minus 3x. When you distribute over here, the 3 is clear, and you pick up minus 2. So over here, you get 4 minus 2x in brackets. You can do it more slowly if you want. That's no problem. Let's look at the constant bin on the right-hand side. On the left, minus 3.17 over 3. The 3's cancel. You pick up minus 17. When you bring it over, it becomes plus 17. And already on the right-hand side, we have minus 25, so it's just a drop down. Okay, and then we simplify inside each bin. 4 minus 2 is 2. 17 minus 25 is minus 8. At the end, you divide both sides by 2, because again, the objective is to solve for x. When you do that, you get x equals negative 4. Transfer the goods over to the left-hand side and insert it where we left off. We left off over here before we transferred to the right, so that's where you do the insertion or the substitution. And we get y equals 17 over 3 is just a drop down. 2/3 drop down, and the x gets replaced by negative 4. Over here, this is not that difficult to deal with. We have 17 over 3 minus 8 over 3, and 17 minus 8 is 9, and then 9 over 3 is 3. Or alternatively, you can do this all in one shot on your calculator if you're still having difficulty dealing with fractions. But to go over it once again, we get 17 over 3. Over here we get minus 8 over 3. We already have a common denominator. So 17 minus 8 is 9, and 9 over 3 is 3. So we conclude that y is equal to 3. And finally, we declare the POI to be negative 4, 3. And now we're in a position to go back to the diagram to verify that everything was done properly. This is the maple generated output. The blue line is line 2, and the red line over here is line 1. So we have line 1 is the red line, and line 2 is the blue line. And you see that they intersect over here. The point of intersection is -4 on the x and 3 on the y. So the POI is -4, 3, as we found algebraically. So we can go on to the next slide. And we have another linear system to solve using MOS, method of substitution. Line 1 is 12.x minus 24.y equals 25. And L2 is -4.x plus 12y equals -11. The first thing I do is look at the coefficients, 12, -24. I don't see a plus or minus x or y. And over here, -4, 12, I don't see a plus minus x or y. And also, I notice that the line 1 over here cannot be reduced. You can't divide through by an integer to reduce it further. And I see the same thing over here, because -4, 12, and -11 has no GCF. So they can't be reduced. So now we're stuck with fractions again. So this is another example where MOS will lead you to using fractions from the outset. Okay, that's one of the disadvantages of using the method of substitution for solving linear systems. So we can zero in on whichever term we want to start off with. We could use the 12x, we can use the -24y, -4x, 12y. Generally, I like to start off with a term which has the smallest coefficient in absolute value. But what did I decide to start off with over here? I'm not quite sure, because I did this problem quite a while ago. I zeroed in on the 12x term. So that's what I did. I left it here. I moved -24.y over to the right-hand side, and 25 is just a drop down. And then the objective over here is to solve for x. So you divide both sides term by 12. When you do that, you get 12x over 12 will give you x. 24 over 12 will give you 2, so we get a 2y. And then 25 over 12 is irreducible. At this point, you transfer the goods over to the right-hand side. And we're going to replace the x over here this time. So method of substitution is all about replacement. And replacement with the use of brackets. Again, no brackets, no go. So we have a -4, and then we replace the x by 2y plus 25 over 12. There it is here, or here it is here. And then we drop the 12y down, we drop the -11 down. So no problem so far. Now I did a rapid backward bin gathering. I opened up a y bin on the left, and I'm scanning only for y terms. I see that -4.2 will give you a -8y, so you drop in a -8. Also, I see I have a 12y here, so you drop in a 12, close up the bin. On the right-hand side, that's the constant bin, we get a -4.25 over 12, which reduces to -25 over 3. And when you transfer it over to the right-hand side, it becomes 25 over 3, and you drop it in. And then we're left with -11 is just a drop down, because we didn't move it. And then you simplify inside each bin. 12 minus 8 is 4. And 25 over 3 minus 11, we get 25 minus 33 over 3, which is -8 over 3. Or you can do this on the calculator if you wish. So at the end over here, we have to divide both sides by 4, and we get y on the left. 8 divided by 4 is 2, so we get y equals -2 over 3. And then we transfer the goods over to the left-hand side, and we left off over here. So the idea here is to replace the y by -2/3, and that's what we do in the next step. So we get x equals 2 bracket, again brackets, minus 2 over 3, close bracket, plus 25 over 12. And then if we expand this, we get a minus 4/3 plus 25 over 12, and that easily reduces to 3/4. Again, we get minus 4/3 plus 25 over 12, which easily reduces to 3/4. And then at the end, we can conclude that the POI has coordinates 3/4, comma, minus 2/3. And then I believe the graph for this is in the next slide. Yes, it is. This slide over here is Maple output. We graphed the linear system using Maple. And line 1 is the red line, and line 2 is the blue line. So line 1, I'm pointing to it here. We have 12x minus 24y equals 25. And line 2, which is the blue line, has equation minus 4x plus 12y equals minus 11. They're both forward slashes because if you look at the coefficients over here, they're opposite signs. And they're opposite signs over here, so they're both forward slashes. Okay, if the signs over here were the same, it would be a backslash. If the signs over here were the same, it would be a backslash. So when the coefficients are both the same sign, we have a backslash. When the coefficients have opposite signs, we have a forward slash. So we find the point of intersection is right here. The x-coordinate is 3/4. And the y-coordinate is minus 2 over 3. And we conclude that the POI is 3/4, comma, minus 2/3. And again, this is the Maple output, which in fact confirms that our MOS procedure was correct. Let's continue. Okay, this is the beginning of the method of elimination. The method of elimination that I use is a little bit different than what they normally do at school. It more or less follows more of a matrix procedure than it does what they do at school. They use a mixed method by and large when you go to school, which consists of half elimination, half back substitution. That's like a hybrid method that I choose not to use. I don't like to crisscross the two methods. Okay, this is a pure elimination method, no back substitution. So my methodology over here is a little bit different than what you've encountered in the past. And basically the procedure is more like a matrix algebra procedure in linear algebra, and I believe that it's more efficient than doing a hybrid solution where you do elimination coupled with a back substitution at the end. So anyway, without further ado, I want to illustrate my method of elimination. Short form is MOE, method of elimination. The first thing to do is to ensure that each line is in standard form. Now, standard form, when we do method of elimination, is of the form a dot x plus b dot y equals c, and we have a constant on the right-hand side. A and b are the coefficients of x and y on the left-hand side. So we'll declare this to be the standard form when we're dealing with the method of elimination. We don't have to leave it in this form. We could move the c over to the left-hand side and have a 0 on the right-hand side. It really wouldn't make any difference, but, you know, I'd rather just follow convention at this point. I'm already very unconventional as it is, so let me put the c over to the right-hand side. So we'll declare this to be standard form. So that's the first thing you should ensure, is that when you're dealing with a 2x2 linear system, the equation of each line is already in standard form. Line 1 over here is minus 2x plus 3y equals 5. Definitely standard form. We don't require the coefficient in front of the x to be positive. That's nonsense. There's no need to do that. Okay, so anything that looks like this is standard form. If you have fractions over here like a, b, and c are fractions, please clear the fractions first. Clear them first, otherwise you're going to create a mess. Okay, so clear the fractions. Or on the other hand, if you have a dot x plus b dot y equals c, and it can be reduced by dividing through by the GCF of all the coefficients, then go ahead and do that first. But over here, we already have standard form, irreducible, so we're good to go. We have standard form, irreducible, good to go. Now, my method of elimination goes like this. I draw a 2-column T-chart, and I title it Eliminate Y, and then Eliminate X. And what I do is I drop down both lines one at a time. I drop down line 1, there's the equation for it. I drop down line 2, there's the equation for it here. What I do is put brackets around each equation. I need to box both equations in, so I put brackets around each equation, and I put dots in front, and I open up empty number bins. Okay, the empty bins will contain the operations that you're going to be performing in order to effect the elimination at hand. Now, so pretend like these bins over here are empty. The 4 and the 3 are not even there. Our job is to zero in on the y terms. Over here we have a 3.y and minus 4.y. There's nothing in common. When there's nothing in common, the idea is to eliminate the y. And by the way, in my elimination process, I never, ever subtract. I always do a linear combination in order to perform the elimination. Always a linear combination with a plus sign in between. What do I mean by a linear combination? Something like 4L1 plus 3L2. I always put a plus sign in between to avoid sign errors. This would be like 4L1 plus 3L2. Okay, now, how do I choose these numbers? How do I choose the coefficients in the linear combination? What I do is I notice there's nothing in common between 4 and 3, so what I do is do a swap. Do not bring the minus sign with you. Just pick up the number, swap it. Pick up the number, swap it. Now test it out. You get a 4.3, which is 12, and 3.-4, which is negative 12. 12 minus 12 is 0, and we just eliminated the y terms. Okay, so let's go over it again. 4.3y is 12y. 3 minus 4y is minus 12y. When you add, the y terms have been eliminated. Okay, so that's the whole idea over here, is to perform a linear combination of L1 and L2 with a plus sign in between. And so we get 4L1 plus 3L2 when we perform that operation, which is always legitimate to perform. We can always take a linear combination of two linear equations and get a valid linear equation. There's never a problem when taking linear combinations. So again, we get a 4.3y, which is 12y, and 3 minus 4y, which is minus 12y. And so these terms are eliminated. And then we proceed with the other ones. I use a Z pattern. 4 minus 2 is minus 8, plus 3.3. Do you see the Z? 4 negative 2 is minus 8, plus 3.3 is 9. So we get minus 8x plus 9x. The y's are gone. Continue distributing. We get a 4.5. We hit the equal sign, by the way. And we get a 4.5, which is 20, and 3.negative 7, which is minus 21. And then all we have to do is collect like terms. On the left, we have 9x minus 8x is just x dot 1. And then on the right-hand side, 20 minus 21 is just minus 1. At the end, you divide. Of course, dividing by 1 does nothing. And we get x equals negative 1. And now we do exactly the same thing on the right-hand side. We repeat the process for x. We're going to eliminate x. So now what do? I drop down the equation for line 1, drop down the equation for line 2, make sure that they're lined up, put brackets around each equation, and now our job is to come up with the linear combination coefficients. To do that, we zero in on the x terms only because the idea is to eliminate the x. We get minus 2x here and 3x here. There are no common factors. Therefore, what I want to do is do a swap. I pick up the 3, swap it in the upper bin. Pick up a 2, swap it down to the lower bin. Okay, so it's always a crisscross. 2 comes down and 3 goes up. Now let's test it out. We get a 3 dot minus 2x, which is minus 6x, and 2 dot 3x, which is 6x. So we get minus 6x plus 6x. Bingo. The x drops out. The x has been eliminated. Okay, again, 3 dot minus 2x is minus 6x. 2 dot 3x is 6x. When you add, the x has been eliminated because minus 6x plus 6x is just 0. And then we proceed with a z pattern. We get a 3 dot 3y, which is 9y, put it down. We get 2 dot minus 4y, which is minus 8y, drop it down. And then we hit the equal sign, and we go to the other side of the equal sign. 3 dot 5, which is 15, drop it down. 2 dot negative 7, which is minus 14, drop it down. And at the end over here, we get 9y minus 8y, which is y dot 1, and 15 minus 14, which is just 1. Divide both sides by 1, and you get y equals 1. And we conclude at the end that the POI has coordinates negative 1, comma 1. Negative 1, comma 1. And then I believe in the next slide, I have a diagram. And here's the maple generated diagram for that linear system that we just solved. Line 1 is the red. It's minus 2x plus 3y equals 5. And line 2 is the blue, which is 3x minus 4y equals minus 7. Over here, the coefficients are opposite, so it's a forward slash. The coefficients are opposite, so it's another forward slash. When I say opposite, I mean opposite signs, okay? So opposite signs for the x and y coefficients, opposite signs for the x and y coefficients mean that the lines are both forward slashes. And of course, the POI is here, and that confirms that x equals negative 1 is the x coordinate, and y equals 1 is the y coordinate. And we conclude that the POI has coordinates negative 1, comma 1. And voila, we're done with that one. We continue with Q16, solution via method of elimination, MOE for short. Again, we first have to ensure that each line is in standard form. A dot x plus b dot y equals c. Make sure it's in reduced form. We would prefer all coefficients a, b, and c to be integers. And so if you do have fractions up here, you must clear the fractions first. And then after you clear the fractions, make sure it's in reduced form. Okay, you want to keep these coefficients a, b, and c as small as possible. And of course, they should be linear, or they should be integer coefficients, and they should be as small as possible so that the method, it becomes a very efficient method. You're not dealing with huge numbers. Let's look at line 1. It's 4.x minus 5.y equals minus 55. It's already in standard form. We have integer coefficients here, and it's irreducible. Let's look at line 2, also standard form. It's minus 3.x plus y equals 22. There are no fractions. They're all integer coefficients, and it's fully reduced. So I declare that to be standard form as well. First off, before we do the elimination, the coefficients over here have opposite signs, so we have a forward slash. The coefficients have opposite signs, so we have another forward slash. So this represents a forward slash, and so does this one here. And now we're going to proceed to the method of elimination. Again, I use a 2-column T-chart, and I do not use a hybrid method where I do elimination on the left and back substitution on the right. I prefer to eliminate on both sides. After all, it is called the method of elimination, not the method of substitution. The high school methods are usually hybrid methods, which I do not prefer. So the idea over here is to eliminate x, eliminate y, and then proceed to eliminate x in turn. So to eliminate y, pick up each standard form and drop it down. Drop down L1, there it is there. Drop down L2, there it is there. Put brackets around each equation and open up linear combination bins out front. So I'm going to call these linear combination bins because these are effectively the scalars of the linear combination. Okay, I know we haven't talked about linear algebra or vectors or anything like that, but these are essentially scalars for the linear combination. So the idea now is to zero in on the y terms. We have a minus 5 dot y and just a y over here. Okay, to eliminate, what I'm going to do is pick up that imaginary 1 and crisscross, drop it inside the bin, pick up that 5, crisscross, drop it inside the bin. And now I test it out to make sure that the y has been eliminated. We do a 1 dot negative 5, which is minus 5, 5 dot 1, which is 5. Of course, minus 5 plus 5 is 0. And voila, the y terms are both gone, so we can proceed. Please check. When you put the numbers in here inside the number bins, please ensure that the y has in fact been eliminated. Because if that is not the case, do not proceed because your answers will be wrong in the end, okay? So please make sure that you check it out because sometimes these require a sign change. So again, y dot minus 5 is minus 5, 5 dot 1 is 5, minus 5 plus 5, bingo, everything's gone. So now I can proceed with the z pattern. We get a 1 dot 4, which is 4, so we get a 4x, and then a 5 dot minus 3, which is minus 15, and we get a minus 15x. Then we hit the equal sign. 1 dot minus 55 is minus 55, drop it down. 5 dot 22 is just 110, drop it down. Now all we have to do is collect like terms. We get a minus 15 plus 4 is minus 11 for the x bin. And for the constant bin, we get 110 minus 55, which is 55. Then divide both sides by minus 11 to solve for x. When we do that, we get x equals negative 5. So we conclude that x is equal to negative 5. Now we repeat the procedure exactly, but this time we eliminate the x. Okay, so we go over to the right-hand side. We pick up line 1, drop it down, pick up line 2, drop it down, put brackets around each line, and leave empty bins out front. The idea now is to eliminate the x, so I examine the x terms. We have a 4 dot x, minus 3 dot x. There are no common factors, so I pick up the 3, put it inside this bin, pick up the 4, put it inside that bin. And now we have to test it out. 3 dot 4 is 12, and 4 dot minus 3 is minus 12. 12 minus 12, bingo, the x is gone. And now we can proceed to do the z pattern. We get a 3 dot minus 5y, which is minus 15y, and we get a 4 dot y, which is just plus 4y. Then we hit the equal sign, and 3 dot minus 55 is minus 165, and 4 dot 22 is just 88. And now it's just a question of simplifying. We open up a y bin, and we pick up minus 15 plus 4, which is minus 11. Then open up a constant bin on the right-hand side, and minus 165 plus 88 is minus 77. At the end, we divide both sides by minus 11 because we want to solve for y. So when we do that, we get y on the left, minus 77 over minus 11 on the right, which is equal to 7. Therefore, we conclude that y is equal to 7. And at the end, we declare the POI to be minus 5, 7. And now in the next slide, we can check to see what Maple got. This is the Maple output for that 2x2 linear system. Again, line 1 is in red and line 2 is in blue. And line 1, you'll recall, is 4.x minus 5.y equals minus 55. Opposite signs, / confirmed. Over here, L2, minus 3y plus y equals 22. The coefficients have opposite signs, / confirmed. And then the POI, at the POI, the x value is -5 and the y value is 7. And we declare the POI to be minus 5, 7, and which is exactly what Maple got down here. Okay, this is the part of the Maple output. And of course, that's what we got through the method of elimination. We conclude that the solution set for that 2x2 linear system consists of a single point, -5, 7. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MATLAB Tutorials in Toronto.